Hello and welcome back to Unbounded Operators, the video series in the field of functional analysis. And in today's part 3, we will define so-called closed operators. Indeed, it will turn out that these closed operators are related to the continuity property bounded operators have. So in some sense, this is the generalization we want now. However, you already know, before we start, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via Patreon. And please don't forget, you can also download quizzes and PDF versions for all the videos with the link in the description. Okay, then let's start again by telling what we mean by an operator. So an operator T is just a linear map between two normed spaces x and y, but we can have a domain. And usually what we do is that we call this domain D of T. So in general, T is not defined on the whole normed space X. But still, it has to be a linear mapping between the two spaces. Okay, and now since this is a well-defined map, we can identify it with its graph. And this you might know, it's just a special subset in the Cartesian product x times y. This means we can simply sketch it into a coordinate system. Hence, in general, you would sketch a graph like that. However, since we have a linear mapping here, we should also make it clear that we have a linear relation as a graph. Moreover, since we work in infinite dimensions, in reality we would expect that the picture looks much more complicated than this line. But still, the general idea here of this set given by the graph of T still holds. Okay, then let's give this set a short name. Let's call it G index T. And now we can define it as a subset of x times y. This means we just have to write down what one point x, y has to fulfill. First, that x lies in the domain of T. And second, we need that Tx is equal to y. So the image of our x is exactly the point y. So not so surprising, this is how in general we would define the graph of a map. However, here we have a little bit more because this Cartesian product here is a normed space again. Hence, it's not just a set, it's a whole vector space where we can also measure lengths. And at this point you should ask, what is the corresponding norm here? In other words, what is the correct length of the pair xy? Indeed, there are different possibilities to do that, but the common one is just to add the two norms we already know. So first take the norm of x and then add the norm of y. And now it's not hard to check at all that this here defines a norm again. Hence, we always have a normed space with the Cartesian product if x and y are normed spaces from the beginning. And therefore, you can say, now in the graph of T, we can also measure distances. Or more precisely, we can use all the topological terms we have for the graph of T. In particular, we can also check if the graph of T is a closed set. And that's exactly what we do now in order to define so-called closed operators. So you see, we call T a closed operator if its graph is a closed set in the normed space x times y. So not a complicated definition at all, we just have to know what closed sets in normed spaces are. And the good thing is, we can assume that we already know a lot. In particular, we know that we can also work with sequences to define closed sets. And this means we immediately get an equivalent definition for a closed operator. More precisely, instead of working with a closed set, we can also work with sequences. So what you have to do is to take an arbitrary sequence xn inside the domain, and this one has to fulfill two properties. So first, it should be a convergent sequence in the normed space X. This means it has a limit that lies in the space X. So we don't have to assume that the limit lies in the domain. And second, we assume that the sequence of the images is also convergent. So Txn converges inside the space y to a limit y. And now the claim is that for each sequence with these two properties, we can conclude two other properties. The first one is, indeed, this limit x lies in the domain of D. And this immediately implies that we are allowed to apply t to this x as well. And then we get the second property, this image is indeed equal to y. So this sounds not so strange, but maybe at this point you can immediately compare this definition to the continuity definition. Indeed, this is what I mentioned before, we want to use this definition as a substitute for the continuity. This is because we already know unbounded operators are not continuous. Okay, now I think we can also write down a proof of this statement from before. So we want to prove the equivalence stated here. And in fact, I already gave you the hint, closed sets can be equivalently described by sequences. So you should know, this works in general in metric spaces, so in particular here in normed spaces. So what you have to do is to take a sequence from the set and you have to assume that this one is convergent. So please don't forget, this means the sequence is convergent in our normed space x times y. So maybe here, let's call the limit also z, and the important thing is, it lies in x times y. Because now the important conclusion here is that this z also lies in gt. So you should see, this is the general thing, closed means you cannot leave the set with sequences from inside. And this is indeed equivalent, all the boundary points already lie inside the set itself. Okay, so this should not be a surprise, and now we want to put this into the context of an operator. So first, instead of Zn, we can already write what we know about the graph. Namely, it always consists of a pair xn txn. So a sequence inside the graph of t always has this form. Okay, and now this sequence should converge to a point in our Cartesian product. And this limit we can just call xy. Okay, but now this claim here tells us that this pair xy also lies in the graph of t. And by the definition of the graph, this exactly means two things. First, our point x lies in the domain, and second, t of x is exactly y. And there you should already see, this is exactly the conclusion in the claim above. And now the only difference here is the assumption from before. However, now we can conclude by the definition of the norm in the Cartesian product that this convergence here is nothing else than this convergence. Indeed, you could say here, if you want to converge to the pair, you have to converge in each component. And converging with the two components is exactly what we have written here. And with that, I would say the proof is good enough. We have this equivalence here. And I would say this sequence definition here is what you should always have in mind when we talk about closed operators. And then it's also no problem at all for you to show the following. Namely, let's consider a bounded operator. In addition, the domain of T should also be the whole space X. So this is an operator like we had it in our functional analysis course before. And in fact, the conclusion here is that such a standard bounded operator is a closed one. So you should see this closed operator notion is so important because it's our generalization from the bounded operators to the unbounded operators as we want it. More precisely, closed operators still have some nice properties the bounded operators had. However, the details for that is something for the next videos. In particular, we will look at examples, we will talk about closable operators, and we will have a look at the so-called closed graph theorem. So I really hope we meet again and have a nice day. Bye bye.